Hey there everybody, welcome back. This is the second set of notes for electrostatics. And in the last video we looked at electric forces, and that is two charges can attract or repel each other at a distance just because of their electrostatic interaction. And so we're going to connect that to the idea of fields. Now, you might remember that gravitational forces and electrostatic forces, they have a lot of similarities. You might also remember that with gravitational forces, we talked about this idea of fields, which is to say that an object, a massive object, might be surrounded by a gravitational field. And if you place an object in that field, then it might experience a force of gravity. Well, we're going to use that same idea to talk about electrostatics, and that's because they are forces that happen without coming in contact. So we do this anytime we run into non-contact forces like gravity, electrostatics, or electromagnetism. And so an electrostatic field is similar to a gravitational field. It's going to depend on the size of and the distance to a charge. So the bigger a charge is and the closer you get to it, the stronger the field is going to be. Now we're going to define an electric field, and we're going to use the symbol capital E. We sometimes put a little arrow over top of the E just to remind ourselves that this E is a vector, and so it's electric field, not, for example, E for energy. And so electric field is equal to the electrostatic force divided by the test charge. So it tells you how many newtons per coulomb you are going to experience. And so E is our electric field. An electric field is going to be measured in newtons per coulomb. Fe is our electrostatic force. And Q is a test charge. So what we mean by that is, if you have a certain charge and you place it in a field, then that charge will experience a force. And the amount of force divided by that test charge tells you the strength of that field. Now, we learned in the last video that we know that electric force is kq1 q2 over r squared. So if I take this and I substitute it in here for electric force and then cancel out the test charge q2, I end up with electric field is k times q1 divided by r squared. And it's just important to kind of recognize the difference between these two. In this case, q1 is the charge that is generating the field. Whereas this Q here is the charge in a field. That's why we call it a test charge. So in the case of electric fields, we're dealing with a force field, which sounds probably a little bit cooler than it actually is. And because forces are vectors, then electric fields are also going to be a vector quantity. And so by that, it means that the direction of the field is going to matter. It's going to be important somehow. And so remember that the difference between electric forces, electrostatic forces, and gravitational forces is that gravitational force is always attracted. So when we talked about gravitational fields, we would calculate the strength of it, but we always kind of knew which way it was going. With electric fields, it's not that simple because we can have attractions or repulsions. So that electric fields can attract or repel. And that just depends on the situation. So we're going to define the direction of an electric field as the direction that a proton would move in that field. So just as a quick example, what do we mean by that? Well, imagine we've got this space, and I come along and I grab a positive charge and put it in this space. You'll notice that that positive charge is surrounded by an electric field, just an array of vectors emanating out from it in all directions. Now remember that the direction of an electric field is going to be the direction a positive charge or a proton would move in that field. So if I take my little test proton and put it in that field, you can see that the direction of the field lines up with the way that proton wants to go. And of course, this is a positive charge, so that proton would want to go away from it. You can see that the strength of the force acting on that proton is going to be increasing the closer I get to it. And that's because the field strength is going to increase the closer that I get to that proton. If I had a negative charge, so a negative charge you could imagine would work in the exact opposite direction. A proton close to a negative charge is going to want to be attracted to it. And so electric field lines are going to go towards a negative charge. So if we were to just kind of sketch that out, imagine that I had a positive charge here. So if this was a positive charge, the electric field lines would be emanating out of the positive charge. So they move out in all directions. Whereas if I compare that to a negative charge, if I have a negative charge here, the field lines are going to be pointing towards that negative charge, because that's the direction that a proton would want to go if you put it in that field. So really quickly, what is the electric field strength at a point where a -2 microcoulomb test charge experiences an electric force of 5.3 times 10 to the -4 newtons? Now just a reminder that a microcoulomb, 1 microcoulomb is equal to 10 to the -6 coulombs. So that's a -2 times 10 to the -6 coulombs. So you'll recall that an electric field is just the force divided by the test charge. And so if it experiences a force of 5.30 times 10 to the -4 newtons, divided by a test charge of 2.00 times 10 to the -6 coulombs, this is going to come out to be 265 newtons per coulomb. Now, a couple of things I want to point out. Just like with forces, you might have noticed that I didn't bother using the negative sign here. And I didn't bother using that negative sign because that's not really going to help me determine what the direction is. I'm going to look at my charge and I'm going to figure out which way the field is emanating at that point, but plugging in a negative there wouldn't really tell me that. So the strength of the field is 265 newtons per coulomb. That means that if you came along in that field at that point and you put a 1 coulomb charge there, it would experience 265 newtons of force, 265 newtons per coulomb. So what would happen to the field strength if you doubled the test charge? Well, if we doubled the test charge, then it would stay the same. The strength of the field does not depend on the test charge. The strength of the field only depends on the charge that is creating the field. So if we double the test charge, that does nothing to the field itself. But if you double the distance, so if you went twice as far away from the origin, you know that the field strength is kq over r squared. If you double the distance r, then the strength of the field is going to be 2 squared, is going to be 4 times smaller. So the field strength, the new field strength would only be 1/4 of E1. And so that would end up being approximately 66 newtons per coulomb. Okay, so we've already seen that individual charged particles are going to emit these fields, and we've seen which way they're going to work. But what happens when two charges interact and their fields start to overlap with each other? Well, if we have two positive charges, so imagine I've got two positive charges, I know that the positive charges are going to, the field lines are going to come out of the positive. But what happens when they interact? Well, I'm just going to go back to this little example here, and you can see it here. If I have two positive charges and I put them together, we can see that when I'm close to this, and so when I have two positive charges and when I put them both in the same space, you can see that the field lines are coming out of the positive charges. So they're coming out of this one positive charge and they're kind of coming out of this other positive charge. But in between, you can see that the strength of the field is actually going to drop down, is going to be 0, because they're working against each other in the middle here. And so when I go back to my picture, my field lines would be coming out of this positive charge in all directions here and here. And same thing with this other positive charge. But then in the middle, they would kind of go and push away from each other and kind of deflect one another. And if these two charges were the exact same strength, then there might be a point directly in between them where the actual field would be zero because they're working against one another. And so what happens if I do the same thing only with negative charges? Well, if I have a single negative charge, all the field lines are going to be going in towards it. If I have another negative charge, the field lines are going to be going towards it. And I can see that again, I get this similar situation where the field lines point towards this one charge or towards the other. But when I'm in between, the field strength is actually going to drop off towards zero. And so if I have two negative charges, the field lines are going inwards towards that negative charge and towards this negative charge. But in between here, they're going to kind of deflect each other. And they're going to kind of go on an angle like this or like this. And in some extreme cases, it might go kind of all the way around like that. And again, I might end up with no field directly in between them. So you'll note that the electric field lines point in all directions. They surround those charges, pointing out everywhere. Anytime we have a situation where two field lines are going to overlap, we simply use vector addition. To find the total. So what would it look like if we tried two opposite charges? Suppose I had one positive charge here and one negative charge. I want you to kind of visualize what that's going to look like. And so what it would look like is I'm going to get rid of this negative charge, and I'll put this negative charge over here. And if I added a positive charge to that, then my overall picture kind of looks like this. And you can see that I've got these field lines that are going out of this positive charge, and over here they're going into the negative charge. But when I'm in between them, they're going from the positive towards the negative. It's like these field lines are pushing to the right and these field lines are pushing to the right, and so overall they're adding up. And so my picture would look sort of like this. I've got field lines coming out of positive and into negative. And here where they line up, they go out of positive and into negative. Kind of like this. And in fact, these lines would loop, some of these lines would loop way, way around and end up coming back down here and so on. Okay, so what is the strength of an electric field midway between a 2 microcoulomb charge and a negative 4 microcoulomb charge? So I'm just going to draw a picture here. Okay, so I've got Q1 is 2 times 10 to the negative 6 coulombs. And then over here, and then over here I've got a negative charge, and Q2 is negative 4 times 10 to the negative 6 coulombs. And they are at a distance that is 0.60 meters apart. And what I'm trying to do is I'm trying to find what is the strength of the electric field at a point right here. I'll call this point P. And you can see that that's located 0.30 meters from that charge, and it's 0.30 meters from that charge. So to find the strength of the field at that point, well, there's going to be two interacting fields, the field from the positive charge and the field from the negative charge. And so I can just look at those individually and then add them up to find the total. So for example, let's think about what E1 looks like. And we'll think of E1 as being the field provided by charge 1, this positive charge. Well, at this point right here, E1 would be to the right because a positive charge placed there would want to move to the right. And what would E2 look like? Well, E2, the field produced by charge number 2, would also be to the right, because a positive charge would want to go towards that negative charge. So I can solve for these individually. And so E1 is going to equal K Q1 over R1 squared. And so that's 9 times 10 to the 9 times 2 times 10 to the negative 6 divided by 0.3, and don't forget to square that. And so this ends up being like 2.0 times 10 to the 5 newtons per coulomb. So 200,000 newtons per coulomb. When I solve for E2, that's K times Q2 divided by R2 squared. And so that's going to be 9 times 10 to the 9 multiplied by 4 times 10 to the negative 6, all divided by 0.3, and again squared. And so this is going to be 4.0 times 10 to the 5 newtons per coulomb. And you'll note again that I didn't use the negative sign in my charge because I already figured out the direction of the field by looking at this picture. I already figured out that that field, both those fields are going to be going to the right. So in this case, to find the total field, if they're both directly to the right, would just be the sum of the individual fields. So in this case, I'll just add them up. And so this would be E1 plus E2, which is going to be 6.0 times 10 to the 5 newtons per coulomb. And if you want, you could say to the right, although I think we kind of captured that in our picture that we drew right there. Okay, one last example. So what happens if we've got fields or forces, for that matter, happening in kind of 2 dimensions? So I've got 2 charges that are sitting here, and I want to figure out what is the magnitude and direction of the electric field at the point P shown down here due to these 2 charges. So I've got these 2 charges, and maybe I'll just call this first one here Q1, and I'll call this charge here Q2. And Q1 is a 12 microcoulomb charge. It's a positive charge. And Q2 is a negative 8 microcoulomb charge. So again, I'm going to use the same idea here. I just have to work in 2 dimensions. And so I'm going to find the individual fields, and then I'm going to add them up and see what my total is. And I think now would be a great time for you to hit pause and try that on your own before I go away and give the solution. And here we go. So what I might do is let's look at E1 first of all. So think about this charge, this positive charge. What is it doing at this point? Well, if I put a proton there at point P, it would want to go away from Q1. So field 1 at this point is going to be downwards because it's a positive charge, so it would push that proton downwards. And so now I'm going to ignore Q1, and I'm just going to think about Q2 and say, okay, well, what will the field from Q2 be doing at that point? Well, if I put a proton there, it would want to go towards that negative charge. So I'm going to have a field this way to the right. And so if I want to find the total, I just have to add them up using vector addition. So find them individually and add them up. And so let's do that now. So E1, field 1 is going to equal K Q1 over R1 squared, which is going to be 9 times 10 to the 9 times 12 times 10 to the negative 6 all over 6.0 squared. And this ends up being about 3,000 newtons per coulomb. Now, by comparison, field 2 is going to be equal to K times Q2 over R2 squared. So that's going to be 9 times 10 to the 9 times 8 times 10 to the negative 6, all divided by 4.5 squared. And when I crunch the numbers on this, I get 3,556 newtons per coulomb. And that number kind of makes sense to me because it is a slightly smaller charge, but it also is a little bit closer. So overall, the field for number 2 is going to be a little bit stronger, and so that works. And so now what we have to recall is that this is these are vectors. And so if we want to find the total, we have to use vector addition. So E1 is this way, and E2 is to the right. So if I want to find the total vector is this one. So there's my total field strength, which again makes sense because if you imagine putting a little proton right there at point P, you can imagine it kind of going down and to the right as it gets away from the positive charge and towards the negative charge. So the total field strength here is just going to be, we'll use Pythagoras, E1 squared plus E2 squared. And when I solve that, I end up with about 4,650 newtons per coulomb. Now, if you're screaming at your screen, no, wait, we can't possibly be done, you're absolutely right, because this is a vector, and so vectors include directions, and in 2 dimensions, that direction is given by that angle. And so theta would equal the inverse of tan of E2 over E1. And this ends up giving us right around 50 degrees. And I mean, I guess you could call that, I don't know, east of south if you want, but I prefer to just kind of look at the picture we've got and then go from there at an angle 50 degrees. And so that would be my solution. Now, the follow-up question to that below here says, okay, what if we put a proton at that point? What would its initial acceleration be? So this kind of gets back to this whole idea of fields. Why are fields useful? Well, this tells me that the field strength at that point is 4,650 newtons per coulomb. That gives me an idea of how much force I will feel per coulomb of charge. If I come along and stick a charge at that point, I already have an idea of how much force it's going to experience. And so I could calculate the force, because force, electric force, is just field strength times charge. If you put a proton there, then you use the charge of a proton. So 4,650 newtons per coulomb times 1.6 times 10 to the negative 19 coulombs means I'm going to experience right around 7.44 times 10 to the negative 16 newtons of force, which is great, except that I want to know the acceleration. And of course, if we assume that gravity is negligible, which on a proton it probably is, the net force would just equal the electric force, which equals ma. And so the acceleration would just equal the electric force divided by the mass. Now the force is 7.44 times 10 to the negative 16 newtons. The mass of a proton is actually given to you on your data sheet, so you have it there for you. It's 1.67 times 10 to the negative 27 kilograms, so it's itty bitty, which means my acceleration comes out at right around 4.5 times 10 to the 11 meters per second squared. Now, it is an acceleration, so I should include the direction, 50 degrees. And so that is my answer for the acceleration. All right, that is it for our video on fields.